so this is problem 61. So it says, this one's kind of fun. While hovering, a typical flying insect applies a average force equal to twice its weight during each downward stroke. Take the mass of the insect to be 10 Gs, or 10 grams. Sorry, not 10 Gs. This is a little different. Assume its wings move at an average downward distance of 1 centimeter during each stroke, and assume that there are 100 downward strokes per second, and then estimate the average power output of the insect. So this one gets really, really complicated really quickly. So let's go over what we are given. So the mass of the insect equals 10 grams, which is equal to 0.01 kilograms. If I'm right, let's see. Yes, 0.01 kilograms. The distance traveled, so we'll say D is equal to 1 centimeter, which is equal to 0.01 meters. Yes, okay. And then the number of times it does it, let's see, the time, I guess, or we'll just put 100 per second. I'm not really sure how to do that otherwise right now. I think that is all we are given. Yeah, so it asks how much power is outputted. So power is measured in watts. Man, that is bad handwriting. So watts is equal to joules per second. And joules are, what is it? Kilogram meters per second squared. So, the first thing we have to do is, and this is also equal to newtons times meters. So that is a terrible end. Let me try that again. Okay, so the first thing we want to do is we want to get newtons because we already have meters. So we know that the downward force from the wings, which is going to actually push the insect upwards, is going to be equal to 2 times its weight. So that's 0.01 times 9.81 for gravity, and then times 2, and that's going to give us our the thing. So that comes out to be 0.01 926. No, just 0.1926. Sorry, my bad. Alright, did I do that right? Hang on a second. Yes. So 0.192. Because... yes. Okay. So that's going to be that many newtons. And then times the distance traveled, which is going to be 0.01 meters, is going to give us, what is that, 0.001926, and that's going to be in joules, because that's force over distance, and then that times 100 for the number of times over seconds. So this is 1 over seconds, or seconds to the -1, either way you want to write it. But 100 per second. And that brings us back up to 0.1926 watts, which is roughly 0.2 watts, which is the answer it gives in the back of the worksheet. There we go. Okay.